Hello, my name is Calin Adrian POPA. I'm from the West University of Timișoara, Romania, and today I'm going to present to you Mittag-Leffler synchronization of fractional order neural networks with leakage delay and mixed delays. So fractional calculus exists for a long time, but only recently it has been applied to the domain of neural networks because of its interesting properties that endow the system with infinite memory, which constitutes a desired property for neural networks. So fractional order neural networks became increasingly studied over the last few years. In electronic implementations of neural networks, on the other hand, time delays are known to occur because of the finite switching speed of the amplifiers. These time delays can often cause instability and chaos in the neural networks, so these time delays are needed in the models of neural networks. New and improved models are introduced on a regular basis, and the fractional order time delay neural networks is without doubt such a model, which has attracted increasing research attention in the recent past. So this paper is concerned with the Mittag-Leffler synchronization of fractional order neural networks with leakage delay and mixed delays. So this Mittag-Leffler synchronization is based on a state feedback control scheme for these networks using the fractional order extension of the Lyapunov direct method for Mittag-Leffler stability. One numerical example is provided to illustrate the theoretical result. So, some preliminaries: the fractional integral of order alpha for an integrable function is given in this way, where gamma is the gamma function. Then the fractional Caputo derivative of order alpha for a function x is defined in this way, and if alpha is between 0 and 1, meaning that n is 1 here, then this is the expression of the fractional Caputo derivative. And the last definition regarding fractional calculus is the definition of the Mittag-Leffler function, which is defined in this way for any complex number z, and when alpha is 1, this reduces to the exponential function. So this means that Mittag-Leffler synchronization is a generalization for fractional order systems of exponential synchronization. So the drive system will be given in this way, where you can see the leakage delay, the time varying delays, and the distributed delays. X here will be the state of the ith neuron at time t. Ci is the self-feedback weight. Aaj is the weight without time delay. Bij the weight with time delay. Gij is the distributed delay weight. Fj represents the nonlinear activation function. Ii is the external input for the ith neuron. Mu is the leakage delay. Tau are the time varying delays, and eta is the distributed delay. We will assume that the time varying delays are bounded, and we defined omega as being the maximum between the leakage delay, the maximum of the time varying delays, and the distributed delay. The initial conditions are given in this way, and for each initial condition function we define the norm as being the supremum norm. Then the response system is correspondingly given in this way, where y is the state of the ith neuron and u represents the controlled input. And this also has initial conditions given in this way. So we denote E as the error between the response system and the drive system, and taking the expression for the drive system and the response system into account, the expression of the error system is given in this way, where f bar is defined in this way. Obviously, for this system, for this error system, we also have the initial condition given in this way. So now we will use the state feedback control scheme to obtain the Mittag-Leffler synchronization between the drive system and the response system, and the controller will be given by this expression, where Ki1, Ki2, Ki3 and Ki4 are the control gains for each I. And with this expression of the controller, the error system has this expression, right? And this can be written in a matrix form in this way, where this represents the Hadamard product. And now we can define the Mittag-Leffler synchronization. So the drive system 1 is Mittag-Leffler synchronized with response system 2 based on the above defined controller if there exist positive constants lambda and beta such that this inequality takes place for all t. So here is where we use the Mittag-Leffler function, which again is a generalization for fractional calculus of the exponential function. And we will also have to make the Lipschitz condition assumption about the activation functions. So all the activation functions satisfy the Lipschitz conditions, where Lj represent the Lipschitz constant, and we denote the diagonal matrix formed with these Lipschitz constants as capital L. Okay, and for our proofs we will need these two lemmas, or these are classical lemmas for fractional order systems, in which in both lemmas we assume that alpha is between 0 and 1. So this means that subsequently we will always assume that alpha, the fractional order, will be between 0 and 1. And this lemma represents the generalization of the Lyapunov direct method to the fractional order calculus. And the main result, so if the assumption about the Lipschitz conditions is satisfied by the activation function, then the drive system 1 is Mittag-Leffler synchronized with response system 2 based on the above defined controller if all these matrices are positive definite. And for the proof, we define the Lyapunov function in this way, and then taking the fractional order derivative of V and for system 6 and using lemma 6, we obtain this. So we have the fractional derivative of V of t, which is less than or equal to this. And here we substitute the expression of the system 6, and then we do a bunch of calculations, and then we use the assumption about so here and here and also here we use the assumption about the activation functions and the Lipschitz which have to satisfy the Lipschitz conditions, and finally we get this inequality. So taking into account the conditions in the theorem, so these conditions about the positive definiteness of these matrices, we obtain that this inequality holds, and by using lemma 7, so by using this lemma, we obtain this here, which is immediately yields this condition, this inequality, which is exactly the condition in definition 4 for the Mittag-Leffler synchronization between drive system 1 and response system 2 based on controller 4, which was defined above, thus ending the proof of our theorem. And now a numerical example. Let's consider that we have the drive system, which is given by the following fractional order neural network with leakage delay and mixed delays. So mixed delays means time varying delays and also distributed delays with two neurons. And the corresponding response system will be given by this expression, and the controller is this one. So it's exactly the controller that we defined earlier. The error is given in this way, and the matrices are these ones. So C, matrix A, matrix B, and matrix G. The activation functions are the sigmoid function, sigmoid functions which satisfy the Lipschitz conditions, and so assumption 5 is satisfied, and L is given in this way because the Lipschitz constant for this sigmoid function is 0.25. And then we can take the leakage delay to be 0.08, time varying delays will have this expression, and distributed delay 0.05. So omega, the maximum of them, will be 0.1. And now the control gain matrices are designed like this, so K1, K2, K3, and K4, and we can easily verify that all these matrices are positive definite, and the minimum eigenvalue of this matrix is 0.1, so 2 times is 0.2. So this means that all the conditions in theorem 8 are satisfied, and this means that drive system 9 is exponentially Mittag-Leffler synchronized with response system 10 based on controller 11, thus ending the application of the theorem 8 on our example. So the state trajectories and phase trajectories for the errors E1 and E2 are presented in the following figures. So for error E1, this is the figure. These are 8 initial values which are depicted with different colors. So you can see that the error tends to 0. Then E2, also for 8 initial values depicted with different colors, and you can also see that the error here tends to 0. And the phase trajectories, so E2 graphed as a function of E1 is given here, also for 8 initial values which are depicted with different colors. So to conclude, one sufficient criterion which ensures the Mittag-Leffler synchronization of fractional order neural networks with leakage delay and mixed delay was given by making the assumption that the activation functions satisfy the Lipschitz conditions. The fractional order extension of the Lyapunov direct method for Mittag-Leffler stability was used to realize the Mittag-Leffler synchronization of the introduced networks based on a general state feedback control scheme. The feasibility and effectiveness of the theoretical results was illustrated by one numerical example. So the method developed in this paper are general and can be used to obtain sufficient criteria for the Mittag-Leffler synchronizations of neural network models with impulsive effects, reaction diffusion terms, or Markovian jump parameters. And these developments will represent promising future work directions. Here are a few references, and thank you for your attention.